Got it? All right. Very good. Let's begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I pray that you just help us today to do correct things and to not waste students' time. Lord, in your name I pray. Amen. All right. I am optimistic that I have chased out my demons in the earlier section, so you may not suffer what they suffered. I'm hopeful. Section 12.5, repair. So, first of all, I should mention to you the definition of absolute convergence. The way I said it yesterday, a little bit muddled. To be clear, a series is absolutely convergent, right, if the series of absolute values converges. All right, so the sum a sub k is absolutely convergent if and only if the series, the sum of absolute value of a sub k converges. Okay. So the first theorem I should have proved yesterday, and I don't know, I just got somehow distracted from this, is that if you have an absolutely convergent series, then you also have a convergent series. In other words, absolute convergence implies convergence. All right, so here's the proof of that. We can all agree that if we have so what we're going to do is we're about to assume that the sum over the absolute value of a sub k converges, okay? And I'll suppose that it starts from 0 just for the sake of specificity. All right. But even before you do that, you have this string of inequalities, right? If I have a sub k, if it's a positive number or if it's a negative number or if it's 0, whatever, it's definitely the case that the absolute value of it is larger or equal to it, right? In the case it's positive. And that minus the absolute value is less than that or equal to it in the case it's negative. Everybody agree? All right, try it out for a positive number, try it out for a negative number, you'll see it's true, both cases. So then, if you add the absolute value of a sub k across this inequality, what do you get? You get 0 is less than a sub k plus the absolute value of a sub k is less than 2 a sub k, 2 absolute value of a sub k, all right? In other words, these guys are what? These are non-negative series, right? Well, non-negative terms, I should say. And the series we form from summing these, is in fact non-negative series, right? So that means that we can use the what? We can use like direct comparison test kind of ideas. Now, that's not quite what we can do here, so let me kind of argue, let me give you an explicit argument for it. All right, so we're going to assume that the series of absolute values converge. What's that tell us? If you look at, let's say, S sub n, which is equal to the sum k equals 0 to n of the absolute value of a sub k, all right, this goes to L as n goes to infinity, right? That's what it means. That's the definition of the series of absolute values converging, right? You guys with me? But what else do we have? So consider that, let's call it, I need another name, let's say T sub n, which is the sum k equals 0 to n of a sub k plus the absolute value of a sub k, right? What's this equal to? I don't think so. No. This, but I mean, you're not totally off. It's related to L, that's true, right? In some sense, but it's this. I mean, by properties of finite sums, we have that, right? So, and of course, that is what? This is what? This is what I'm calling Sn again, right? This is the nth partial sum of the absolute value series. So you could solve this, right? I suppose. So we could say, therefore, what? The sum k equals 0 to n of a sub k is equal to what? It's equal to Tn, right? Which is a thing, minus Sn, right? Now we know that S sub n goes to L, right? Because that's tantamount to the convergence of the absolute value series. How can I argue that T sub n also converges to something? Consider, right? 0 less than or equal to a sub k plus the absolute value of a sub k less than or equal to 2 times the absolute value of a sub k implies what? That implies that the series a sub k plus the absolute value of a sub k, k equals 0 to infinity, converges by basic comparison test with the sum of 2 times the absolute value of a sub k, which is actually equal to what? We can pull the 2 out, right? Multiplication, scalar multiplication by 2 does not change the convergence or divergence of the series, and so this is we know this converges, right? So therefore, what? Thus, Tn converges to T in the reals for some T, right? N goes to infinity. And therefore, the sum k equals 0 to infinity of, a sub k is going to just be equal to T minus L. It converges to that. What was it? Did I misspell something? Or was it just was my font did my font degenerate into something ununderstandable? What is my K's look like N's? Yeah. Sorry. Yeah. Yeah, I'm not really fond of the letter K. I really prefer to do all of this stuff with N. But I'm trying to behave and follow the book. So yeah, there we go. K. At least we're not also using kappa. If we were using K and kappa, what I'm doing right now would be indefensible. So do you see that proves it, right? So if we have absolute convergence, that implies convergence. Yes, sir. Infinity. Notice that I'm using T and L. Those are actually the limits of the sequence of partial sums there. See, my argument is that the T sub n goes to T, S sub n goes to L, so this goes to T minus L, which is what we want, which is that the series converges. Okay, so proof aside, the reason we prove things in here is just so that they're not just a black box. Also, the proofs we go over, believe it or not, the steps we make in the proofs are the same steps that you need to make to solve certain problems. And I don't think you can really understand the theory as deeply as you need to without seeing a good subset of these proofs. So that's why we cover them. But here is an example of where that theorem would be useful. Let me get rid of this minus 1 to the n. This, if you see a problem like this should shout at you, integral test, right? Now, that is only going to be echoing in your brain if you have settled U substitutions, right? if you are confident about how to do U substitutions, you should immediately recognize this. If you change it, right, you should be like, aha, that's just minus 1/2 e to the minus x squared, right? Just make a u equals to minus x squared substitution, bam. And that's nice because, well, that's a continuous positive decreasing function, I believe. The exponential wins, yeah. And so I can apply the integral test, right? I do believe you can show the integral test, and that'll show that, in fact, this series converges by integral test, okay? However, if I muddy up this example a little bit with one of these guys, like so, then I can't use the integral test on that example, can I? No, I cannot. But what do? I take the absolute value of it. I show that the absolute value of the series converges by the integral test. And then by this theorem, I have the thing with the plus minus plus minus plus minus converges. But probably it would be easier just to use the alternating series test. Okay. That said, I mean, I don't think that's really the right way to do this problem. I mean, if I have a minus 1 to the n, I probably can just be like, let me put it in the other notation. This would be the sum, you know, k equals 1 to infinity of k e to the minus k squared times minus 1 to the, let's say, k plus 1. All right. So this is like b sub k if we started at 1. And you can see that that's positive, and you could show that it's decreasing. And you can also show that this is k over ek squared, right? Which by one application of L'Hopital's rule, extending k to be continuous, right, is 1 over 2k e to the k squared by chain rule, right? Which goes to 0. So therefore, by the alternating series test, you know, the series converges. Now, this is a partial solution, okay? I'm being brief here. I should really, of course, actually show that b sub k is positive and decreasing to be more complete in my solution. But that's probably a faster way to solve that problem, though, truth be told. All right, let me move on here. Any question, though, before I go on? Yep. When it what? Yeah. A sequence which goes 1 minus 1, 1 minus 1, 1 minus 1, yeah, that's a divergent sequence. When we have a series which has terms which are oscillating, like plus minus plus minus plus minus terms, but those terms are also getting small, the sequence of partial sums, right, can actually be converging to something. So it is true that the nth term the kth term in the series has to go to 0 if it's going to be convergent. But whether or not the series is convergent is totally governed by the convergence or divergence of not the term in the series, but the sequence of partial sums for the series, right? So, but even so, this isn't like that. It's not that it's going plus or minus 1. It's going plus or minus 0.1, plus or minus 0.001, plus or minus 0.001, plus or minus, you know, it's getting. Do you guys have any questions about number 25 in the homework? Here's number 25 from section 12.1. We talked about that earlier. Rewrite this in sigma notation. There it is. So how zoomed in is that? Is it like, can you see that up there? No? Okay. This one was what? This is like section 12.2 number something? I forget. This is one of your other homework problems. This is an interesting example. It's to rewrite x over 1 plus x as a series. How do you do that? Well, remember we know geometric series. So this is really just a problem of pattern matching. So I know that if I have this geometric series, which by the way is sum k equals 0 to infinity of ar to the k, Well, that's equal to a over 1 minus r, provided that the ratio is magnitude less than 1. So if I'm trying to rewrite something like this as a series, what I do is I just think this is like a geometric series, the answer for a geometric series. So I just kind of have to work backwards and identify what's A and what's R. So I just do pattern matching. I just say, okay, well, I'm going to rewrite this as 1 minus minus x, right? And then, so I can see A is equal to x, right? And R is equal to what? Minus x, right? And then geometric series, again, working backwards. And then just clean it up. That's minus 1 to the k times x to the k plus 1. K equals 0 to infinity. Or if you want to write it out explicitly, x minus x squared plus x cubed minus x to the 4th plus dot, 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 dot. This is where we're going. This is what we want to understand and actually do following today, is to take a function, right, in this case f of x, this rational function, and replace it with an unending polynomial. See, the geometric series already does that for us, for this particular example. Isn't that neat? Instead of looking at this complicated fraction of x's, I can look at this very simple unending polynomial of x's. Okay, it's, I mean, you can, okay, I'm being a little bit facetious. But, you know, that is nevertheless a very, very useful way of looking at this function in terms of this series, which is called a power series, by the way. 12.2. I know, I'm sorry. You guys already did this homework like Tuesday of break. Oh, thanks. Lost in. I have very short-term memory. If I can't derive it, there's not much hope. So, I know you guys did this like Tuesday of break, so you've forgotten this problem already because you did it so long ago that it's not fresh in your memory, but there's how you do it. This one, I think we even talked about this one before in here. Did we talk about this one already? I think we might have, but. All right. Next. As you guys pointed out, my proof of the alternating series test yesterday was just wrong. Oh. Just wrong. And then I got talked into something else which was equally wrong, but seductively interesting after class, and then I bought into it, and then I just tried to prove that in the earlier section. Of course, that blew up in my face. So this is my fourth attempt. The alternating series test. I think 4 is a charm. All right, here it is. Given B0, B1, B2, positive, and decreasing, we have that the sum k equals 0 to infinity of minus 1 to the k, b sub k, converges if and only if b sub k goes to 0. All right, this is the alternating series test. First of all, this direction. If the series converges, right? Then minus 1 to the k times bk goes to 0 by kth term test, right? Therefore, b sub k goes to 0. That's it for the first direction. That we did correctly yesterday. I did that correctly in both sections, actually. It's the other direction which is giving me fits. All right, here we go. The other direction. Assume that the kth term goes to 0. All right. I was not far off from the correct proof in here yesterday, not too far off. I just have to be careful about what I'm doing. We want to consider the even and odd subsequences of Sn. So like, we'll let C sub j will be equal to S2j, and we'll let, I need some other letter, eta I guess is what I used, right? And let eta sub j equal to S2j plus 1, I suppose. I now want to argue that the even and odd subsequences, well, let's just argue. So let me be careful. So first of all, C sub j is what? C sub j is S sub 2j, right? Which, by the way, is, as we argued yesterday, B0 minus B1 plus B2 minus B3 plus plus what? Plus B sub 2j minus 2 plus B, rather minus, right? 2j what? Minus 1 plus B sub 2j. And since the b's are decreasing, as we saw yesterday, this is positive, right? This is positive. All these things I'm grouping in green, these are all positive, right? Positive, positive, positive. These are all positive, right? Since the b sub k is what? It is greater. Excuse me, it is less than, it depends on how I'm going to write this. This is less than b sub k minus 1, right? It's decreasing. I guess I should probably write this as b sub k minus 1 is less, no, is what? It's greater than b sub k, is that right? If I go on, I get smaller. So these differences are all positive, right? And then what are we doing at the end? We're adding this, but this is also positive, right, by assumption? This is true for any j, right? So this is greater than 0. So therefore, C sub j is positive sequence, right? We got that last time. Where I got confused was to not look at the right thing. If we look at C sub what? So I should look at maybe C sub j plus 1 perhaps. What would that be? S sub 2j plus 1, right? Parentheses. Which would be what? S sub 2j plus 2. What's that? I'm sorry?
You said like C sub j equals S sub 2j and M sub j equals S sub 2j.
Oh, perhaps, but I don't care. That's part of my confusion yesterday, was trying to do both at once. But I'm going to steer away from that. I'm focusing here right now on the even subsequence, okay? What I'm trying to show right now is that it's in fact a positive, what?
Decreasing.
Yeah, positive decreasing sequence, right? Bounded below by 0. right? Which we'll say by the bounded monotonic sequence theorem, it converges to its greatest lower bound. Now that doesn't have to be 0, but it has to be something. What that something is depends on the details of the actual series, right? But I need to show that this is what is this though? This is equal to what? This is equal to, you know, well, this is equal to S sub 2j plus what? Minus b sub 2j plus 1 plus b sub 2j, right? Do you guys see what I did there? If you look at the 2j plus 1 partial sum of the series, you go all the way to j, and then you add the next two terms, which happen to be minus the odd term plus the even term, right? Yes. Thank you. I was about to get very confused again. Okay, so what can we say about this term? Is that positive or negative? Let's see, 2j plus 2 is further down the line than 2j plus 1, right? So in terms of magnitude, that is smaller than this. So this is a negative number, since b is decreasing, right? That is a number. That is a number. This sharp nonsense you're talking about, and this hashtag thing you're talking about, has no place in this room. No, sharp is fine. I'll accept the sharp. Let's see here. What do we got? Okay, so what this is, right, is this is equal to what? This is equal to Cj minus, let's say, epsilon, where epsilon is greater than 0. Epsilon is just some number, or hashtag. Sorry. So what can you say? Does this show that Cj is increasing or decreasing? We've shown that the j plus 1th one is what? Smaller than the jth term, right? Therefore, C sub j is decreasing. Consequently, hence, C sub j converges to C. Well, let's say it converges to L for, what do I want here? You know, or S sub 2j converges to L as j goes to infinity. Now we'll go back to what Travis was saying, all right, and we'll relate the odd partial sum to the even partial sum, all right? So like, so the eta, right? Eta sub j was what? It was, we said S sub 2j plus 1, right? Which, by the way, would be what? This would also be equal to S sub 2j, right? Minus b sub what? 2j plus 1. Now, so what do you get then? So this is the hard work. We don't have to work so hard for this one. Hence, eta sub j goes to what? L minus 0 as j goes to infinity, right? By that, just this goes to L, that goes to 0. Because we're assuming that the b sub j goes to 0, right? That's where we finally used that the limit of the b sub k goes to 0. We hadn't used that up to this point, right? So now what we've shown then is that both the even subsequence and the odd subsequence of the sequence of partial sums, they're both converging to L. So thus, S sub n goes to L as S sub 2j and S sub 2j plus 1 both go to L as j goes to infinity. Now that's a problem that was proved earlier in the homework. I didn't assign it to you guys, but if you can show both the even terms and the odd terms go to the same thing, if both the even subsequence and the odd subsequence of a given sequence both go to the same value, then the sequence also goes to that value. We actually saw these things, and you can let's see here. We actually, remember we looked at this alternating series? Like here's 1, right? And so here's 0, here's a half, right? And then in here somewhere was like natural log of 2. Remember how that worked? So we had, this was like S1, right? This is S2. 5/6 was S3, if I remember right. And then S4 was like over here, right? And then, so I should probably use some color coding, but you know, these guys, this was the S sub 2j. Oh man, I did it again, didn't I? Oh, my index. See the, dang it. This is for this, this guy, right? Minus 1 to the k plus 1 over k. K equals to 1 to infinity. So the trouble with this is it starts out with 1 minus a half plus a third minus a fourth and so forth. So in this one, the even subsequence increases to L, and the odd subsequence over here decreases to L. So it's, but it's because the indexing is not quite set up the same. So, yeah. They both, one converges to the natural log of 2 from below, the other one converges to the natural log of 2 from above. So the even sequence takes the L, this is actually the greatest lower bound of the range of what I called Cj. In other words, L is less than or equal to Cj for all j. And it decreases to L, the even subsequence there. Conversely, the odd subsequence is below L, and it takes L as its least upper bound. And they meet in the middle. That's what the proof really is. I feel better, sorry. I know you guys don't care that much about the proofs, but it's like a splinter in my mind until I get it out. All right, fine. I feel better. Now let's get back to your homework. How about that? So. No? This one? No? No homework? I mean, we could do more proofs. Oh, homework's good. Okay. Oh, finally. Oh. Then, I'm sorry, there's there's like the finishing blow here. So you notice that if you look at Sn minus Sn minus 1, that has to be less than or equal to b sub n. I'll just let you read the book. I know I've proved enough today, but if you understand what we did here, his proof that this it follows immediately from our argument, it's really, really easy to understand if you just focus on that paragraph on page 599. As he said, we show the partial sums of even index decrease towards L, the partial sums of odd index increase towards L. So that means L lies between even and odd subsequences, right? Sorry, somebody just ran past the window. It weirds me out. And so that means that the difference between n and n plus 1 has to be less than a sub n plus 1, which in this case is b sub n. And anyway, just look at the bottom of page 599. That proof is understandable if you understand the proof now. It actually is. It's clear. When I first read that proof of the estimation theorem, it didn't make sense to me. But now it does, after I understand this proof. Anyway, your homework, which you guys have questions about? Don't all speak at once. Yep.
Is the next homework section still due the date that you sent out in that email?
I think so. It kind of depends on what happens tomorrow and Friday, but. Yep. 12.2, number 4. Find the sum. Oh, say 1 over. Oh, man, it's been a while since we talked about this one. It feels like forever ago that we talked about this kind of problem. And it starts where? Okay, so what you want to do here is, this is equal to the limit, of course, as n goes to infinity of what? The sum, k equals 0 to n, 1 over k plus 3 times k plus 1 times k plus 3, right? We can actually find a formula for this. Via partial fractions. And telescoping series. So let's see here. You guys tell me, 1 over k plus 1 times k plus 3. Let's just, I don't want to work this out. You work this out, okay? It's like a over k plus 1, right? Plus b over k plus 3, right? Except that one of these is going to be negative, so I'm going to write it this way. Okay. So then the sum, maybe work this out so I can put numbers in there so it'd be less confusing. They're ones? Oh, so I'll bring a half out here. Hey. If you got a half on both of them, put the half out front. Nobody wants to write halves on everything, right? So k equals 0 to n is what? This is 1/2. And so like k equals 0 gives me what? 1 minus 1/3. And then k equals to 1 gives me 1/2 minus 1/4. And then what's k equals? K equals 2 gives me 1/3 minus 1/5. And this goes on. And it looks to me like there's going to be a cancellation that starts where? The 1/3 goes. The 1/4 goes with something I haven't written yet, right? The 1/5 goes with something. Okay, fine. So all that remains is this and that. There's going to be a symmetry here. The end game is the same. So if I keep the last two terms, keep the last two terms in here, I should get the total story. So what's the last two terms? N minus 1, which gives me what? 1 over n, minus 1 over n plus 2, plus what? 1 over n plus 1, minus 1 over n plus 3. And so basically, what survives the telescoping is just the very last term and that one, these guys. So in other words, what we find, the formula is exactly what? The formula is 1/2 of what? 3/2 minus 1 over n plus 2 minus 1 over n plus 3. And you see, you can actually take the limit as n goes to infinity of that explicitly, and hence determine not only that it converges, but also the value to which it converges, which is what? Yes. This is the other standard elementary example of a series which not only converges, but you can actually calculate its sum. There really only are two examples I know of at the elementary level where this happens: geometric or telescoping. Anything else that I know of is just some kind of like combination of these things. You know, you can take sum of geometric series, which wouldn't be geometric, but they're built from geometric series, stuff like that. But yes, sir. 12.3, number 14. Oh, that's almost the same as this one. Wait a minute, 12.2 or 12.3? Oh, sorry. Yeah, 12.2, number 14 was like the doppelganger for that number 16 there. 12.3, number 14, on the other hand. What's that one? Oh, this one. We talked about this. So we did direct comparison. You got to do direct, well, at least one way to do it is do a direct comparison to 1 over. So 1 over 1 plus 2 ln k. We showed yesterday that this is, in fact, greater than or equal to 1 over 2k. Hence, the series 1 over 1 plus 2k diverges by basic comparison test with respect to the sum of 1 over 2k. You know, this is, by the way, I mean, so of course, this series k equals 1 to infinity of 1 over 2k is equal to 1 over 2 times the series k equals 1 to infinity of 1 over k, and this is p equals 1, right, diverges. This, not super obvious. And if you look at what we did yesterday, I showed the details there. I will post that sometime later today, sorry. As soon as I can, I'll upload that. I went through it more carefully, I think, in the earlier section. But I also went through it in here. Yep. I'm sorry?
Is it 1 over 1 plus 2k less than 1 over 2k? So
Less than? I hope not, because I need something smaller diverges, if I'm going to say it diverges by basic comparison test.
is it smaller? 1 over 1 plus 2k than 1 over 2k? Because you're adding a 1 to the denominator.
It's natural log versus k.
But what about the second line?
No, the second basic comparison, right? First basic.
There's only one basic comparison here. What are you guys talking about?
Do you mean that that's the 1 over 1 plus 2 ln of k?
Oh, yeah. Oh, I'm sorry. Yes, that's supposed to be ln k. Thank you. Yeah. Very good. Yes, sir. I'm sorry, not sir. Yes. My default is to say yes, sir, and unless you're a Peanuts character, it's not really appropriate. Let's see here. What's that? 12.3, 40. So you got to use number 40, right? I was hopeful to justify number 40 today, but I just don't have time. But it is just that inequality we looked at from the integral test is what justifies that. The pictures we drew with upper and lower sums below and above the integral as they relate to the series going from n to n minus 1, you play around with that. Eventually you get number 40. You don't have to do number 40. You can use number 40 to do number 44 is the point there. But you're still lost on how to actually do that? Okay. Yeah. But you see, I mean, for those of you who don't have it right in front of you, we're talking about how do you estimate the error in like the 100th partial sum for the p equals 3 series, right? So here's a kind of funny thing. Check this out. If I was to ask you what's the error if I say k equals 1 to 100 of minus 1 to the k plus 1 over k cubed, right? So if I was to ask you, if I was to compare k equals 1 to infinity, minus 1 to the k plus 1 over k cubed, right? If I was to ask you, what is this, at most, the error, right, in the 100th partial sum, what is it? What's that? I couldn't hear you. Right, the 101. So it's just 1 over 101 cubed. It's just the next thing you're not using. Why can't we do that? Why can't we do that in problem 44? Problem 44 is not alternating, right? So problem 44 forces us to use a more sophisticated error estimation technique, which is based on the integral test. There is an integral test, approximation test, that I was hoping to share with you guys today, but I haven't had a chance to find it and state it carefully, so I can't do it. But essentially, you can redo problem 40 for other functions. I think he may be saving that for the Taylor series sections. It may be built. It's either in the exercises as we go on, or he does some careful estimation formula for Taylor's theorem. Maybe it's covered there somehow. He doesn't usually leave things out. He just doesn't tend to cover things multiple times. If he can weave it into something else, he won't cover it earlier. Oh, well, I guess our time is up. So I will